Hello and welcome to the next part of potential and current dividers, this time looking at a real application of the potential divider formula to the problem of circuit loading. Circuit loading is the issue that the output of a circuit can change when another circuit is connected to it. Probably the best way to see this is to investigate it in the simulator. So let's have a look at that. Okay, here we have a circuit which has an output that can be modelled like this. A voltage source, of 1 volt in this case, going through a resistor of 500 ohms. Now, many real circuits do have a resistance like this on its output for a number of reasons. Sometimes it's to protect the output stage. If there was no resistor here and the output was accidentally shorted to ground, then there would be, in theory, an infinite current flowing out of here, and that could damage the output stage of the circuit. Other circuits have an inherent resistance there just due to the way they are manufactured. And I'm thinking here of things like microphones or electric guitars, where the voltage is produced by a transducer that has an inherent resistance in it. Now, if I just take a voltmeter and measure the output of this circuit at the moment, you'll see that it reads 1 volt. And that's because there is no current flowing. None at all. If I turn on the current, I'll see it's 0. And there's no current flowing because there's nowhere for the current to flow. An ideal voltmeter like this has an infinite resistance, so there's no current flowing down through there. It can't flow this way because the switch is open. So, with no current flowing, there is no voltage drop across this resistor. That's just Ohm's law. Delta V equals I times R. If I is 0, then delta V is 0 as well. If delta V is 0, then the voltage on this side is the same as the voltage on this side. It's just 1 volt. Until I connect something to the output stage. And in this case, I've got a circuit with an input resistance of 1K that I'm about to connect to the output stage of this circuit. And I've just measured the output voltage of this circuit and found it to be 1 volt. So, I connect my input stage to the output of this circuit, and the output is no longer 1 volt. It's dropped. And that's because this is a potential divider. Voltage here, 1 volt, current flowing through 2 resistors down to ground, and the middle point of those 2 resistors, which is the output of the potential divider, is the input to circuit B. It's the voltage that circuit B is actually seeing at its input, and it's substantially dropped from 1 volt in this case. And this usually isn't what you want. If you design a circuit with an output voltage of 1 volt, you would like that output voltage to get to the input of the next stage. In this case, it doesn't. Ways we can help. We could reduce the output there. It's not always possible. If that output stage was something like a high impedance microphone, we wouldn't be able to do that. But if it's many other types of circuitry where we've intentionally put in a resistance to limit the output current, then we can reduce that resistance a little bit. That, as you see, gets our output voltage here, which is the input voltage to the next stage, much closer to our 1 volt. The other way to do it is to raise the input of the next stage. If I took that up to 100k, then once again, I've got my input voltage much closer to 1 volt, because most of that 1 volt drops across this 100k resistor, not so much across the 500 ohms. Just apply the potential divider formula, and you'll see that the voltage here is this resistance divided by the sum of the 2 resistances. Well, 100k divided by 100,000 plus 500 ohms is very close to 1. So this is very close to the 1 volt that we have here. Once again, we can't always do that. Sometimes circuit B's input stage has a small resistance, and there's nothing we can do about it. For example, it could be a pair of headphones, which have an impedance of 32 ohms. And you can't raise it up without reducing the volume that people would hear. And in this case, if we had an audio amplifier with an output of 500 ohms, then we'd be getting very little voltage across our headphones, our 32 ohm headphones. There's another reason that we often don't want the input resistance to be particularly high that will come across much later in the module, and that's the problem of noise. A high input impedance tends to make this circuitry noisier. So if this was a very high specification sensitive microphone amplifier or something like that, we wouldn't want that to be a very large resistance. It would reduce the noise performance of our amplifier. So we've got to look at our application and weigh off all of these trade-offs and to work out what the optimum input and output resistances should be set to for any particular circuit. It can be an interesting problem, but like a lot of things in engineering, the optimum solution is a trade-off between competing arguments. Okay, that's all I wanted to say about this one. Comparatively short little topic. Next time we're looking at an extension of the potential divider equation to the case where you have more than one voltage input, and that's called Millman's theorem.